everybody, and welcome to MHA's Medical Math Playlist. My name is Mr. Christian, and I'm here to teach you some math. Now, the kind of math that we're going to explore in this course is not just limited to pharmacy technicians or medical assistantship, but really any math area within any medical field you can think of. As I said before, my name is Mr. Christian. I have 20 years experience as a pharmacy technician. I am an instructor here at Michigan Healthcare Academy where I teach the pharmacy technician course, and I also have a degree in physics and mathematics. So with that being said, let's do some math. Hi everybody, and welcome back to another video on MHA's Medical Math Playlist. Today we're going to be exploring a very common math problem you're going to find in the pharmacy technician field. So without further ado, let's go to the board and figure out together, shall we? So we have a problem that says, well, we have an order that comes in from a patient and it says amoxicillin 250 milligrams per 5 mLs. The SIG on the order reads the following: 1 teaspoon by mouth 3 times a day for 10 days. The first question we need to ask ourselves is, what is the quantity in mLs needed to fulfill this order? So let's figure that out. You see, how I like to do math is I like to divide it into 3 sections. What do we know? What do we want? And then where do we start? And what do we know is just going to list off the variables and the pieces of information that we have at our disposal. What do we want is going to list our goal. What's our end goal? What do we want from this problem? And then where do we start is where we actually begin to solve the problem. With everything listed, the math should fall into place. Let's do that together. So what do we know? Reading from left to right, we know that the patient gets 1 teaspoon by mouth. That's 1 teaspoon every dose, right? So they get 1 teaspoon for every dose. The next piece of information we can extrapolate here is the fact that the patient gets it 3 times a day. Well, what do they get 3 times a day? They get 3 doses a day. So 3 doses per day. And then the last piece of information we have here is for how long? How long is the patient taking this medication? Well, they're taking it for 10 days. So 10 days. Perfect. Now, the problem 1 asks, what is the quantity in mLs needed? So what do we want? We want mLs. But there's something missing here. We don't have mLs anywhere in the information that we have listed for no. So how do we fix that? Well, what else do we know that is not necessarily listed in the problem? A conversion factor. And that conversion factor is there is 5 mLs for every 1 teaspoon. And that should help us solve the problem. So where do we start? We always want to start with something that relates to what we want. So is mLs anywhere in here? Yes, it's right here. This piece of information holds a piece of what we want. So let's start with this. So 5 mLs for over 1 teaspoon. We can knock that out. Okay, great. Now using dimensional analysis, we want to cancel out this teaspoon here, right? So how do we cancel out that teaspoon? Is there a teaspoon anywhere in the pieces of information that we know? Yes, right here. So let's bring that down, right here. So 1 teaspoon for every dose. Perfect. Now let's knock out this dose. We have doses here, so that'll cancel. Let's move that down here. So 3 doses for every day. Perfect. Last piece of information is days, because that'll cancel out days here. Perfect. So now, using dimensional analysis, we can go ahead and start canceling out the dimensions. So days cancel days, doses cancel doses, and teaspoons cancel teaspoons. What are we left with? We're left with mLs, which is what we want. So let's just do the math. 5 times 1 times 3 times 10 all over 1 times 1 times 1. Doing that across, 5 times 1 is 5, times 3 is 15, times 10 is 150. So the answer is 150 mLs. And that answers questions 1. And that answers question 1. So we do know that there's 75 mLs for every 1 bottle. And we also know that there's 150 mLs needed to fulfill the whole order. But what do we want? We want bottles. Okay, so where do we start? Well, we want to start with something we know. Well, we know that this contains bottles, but it's inversed. That's okay, because it's a proportion. There's 75 mLs for every 1 bottle, and for every 1 bottle, there's 75 mLs. Using that proportion, we can simply flip it to read 1 bottle for every 75 mLs. Perfect. So that gets rid of that. But how do we get rid of these mLs? Well, we simply multiply it by our other variable that we know, the 150 mLs up here. Because we'll find that the mLs cancel mLs, and we're left with bottles, which is what we want. Therefore, let's do the math. 1 times 150 divided by 75. 75 goes into 150 2 times, therefore the answer is 2 bottles. And there you have it. 150 mLs to satisfy the order, and 2 bottles would be needed to completely fill and dispense it. Hi everybody, and welcome to another medical math video with MHA's playlist. My name is Mr. Christian, and today we're going to be looking at a very famous, typical pharmacy problem that technicians encounter every single day. It's dealing with everyone's favorite steroid, prednisone. Now, prednisone is a special steroid in that it's usually dispensed in tapered dosing. And this is very common for a technician to get an order of this scale where they will need to figure out the quantity that they'll need in order. So the SIG reads as following: 3 tablets by mouth 3 times a day for 3 days, then 2 tablets by mouth twice a day for 2 days, then 1 tablet by mouth every day for 1 day, then 1/2 tablet by mouth once a day for 1 day. The question is how many tablets would be needed for this order to be dispensed? Let's go to the board. So problems like this are pretty simple in that the math is pretty much laid out for you. If we know that we're taking 3 tablets and it's 3 times a day for how many days? 3. Then we can simply multiply across. So 3 times 3 times 3 is going to give us 27. Then 2 times 2 times 2. So 2 times 2 times 2. And that's going to give us 8. Then 1 times 1 times 1. So 1 times 1 times 1 is going to give us 1. And then 1/2 times 1 times 1. So 1/2 times 1 times 1 is going to be 1/2. So if we're adding this together, we can see that 8 plus 27 is going to give us 35, plus 1 is going to give us 36, plus half of that is going to give us 36.5 tablets. But you can't just dispense half a tablet unless you cut it in half. Sometimes in pharmacy we actually round up. So this can be rounded up to 37 tablets. And there you have it. Hi, and welcome back to another medical math video with MHA. My name is Mr. Christian, and today we're going to be doing another math problem. The math problem in question is a very common problem that pharmacy technicians may encounter in the field, or at the very least, may have to derive on the national exam. So, the question is, what should the last digit read to make this a valid DEA number? So the DEA number on a prescription is used whenever a physician writes for a controlled substance. There are times when a technician will need to validate to ensure that this is a valid DEA number. The first thing you want to check is, does the second letter match the first initial of the physician's last name? Assuming that that is correct, you can go ahead and verify the math. Now here I've left the last digit blank. Sometimes you may encounter a scenario where there is a digit there and you need to verify that the digit is correct. But in this case, I've left it blank. So let's calculate it together. Let's go to the board. So the formula for calculating a valid DDA number is you take the first, the third, and the fifth problem, or the fifth number, and you add them together. So here you get 1 plus 7 plus 4. And in doing that, you get 12. Then you take the second, the fourth, and the sixth problem, and you add those together as well. So you get 5 plus 6 plus 2. And what you're left with is 13. But for this section, when dealing with the even number numbers, you have to take the number that you get and you have to double it. So 13 times 2. In that case, you get 26. Then you have to add the number you got for the odds and the number you calculated for the evens. So you get 12 plus 26. And that gives you 38. And the last piece of information is the last digit that encompasses that number when you add these together should be the last digit here. So if this is 8, that means that this should be 8 as well. And there you have it. Hello everyone, and welcome to another MHA math video, where today I'm going to be showing you a pretty common compounding problem that pharmacy technicians may encounter in the field. It's divided into two parts. So the technician receives an order for ibuprofen 2% gel. The first question that needs to be asked is, how many milligrams of active ingredient will be needed to compound 200 grams? So let's start there. But you'll notice I underlined milligrams for a reason. So how we start this problem is we're going to translate what is written into math. So the first thing we want to ask ourselves is, what is 2% of 200 grams? So that's what we want to ask ourselves is 2% represents the strength, the concentration of the compound in question. And that's indicative of the active ingredient. So how do we calculate that? Well, how much of that 200 grams is active ingredient? And we do that by multiplying it by the percentage. So let's translate this together. So what is our variable, x? Is our equal sign. 2% becomes a decimal. Of is multiply, and then 200 grams just comes down. So x is equal to 0.02 times 200. And as we can see, 0.02 times 200 is simply 4. But for what? The unit up here is grams. So x is 4 grams. But that's not the end of the story. This is for problem 1. That's not the end of the story, because we're asked for milligrams. So there is 1,000 milligrams for every 1 gram. And what we have is 4 grams here. Therefore, grams cancel grams. We're left with milligrams, which is what we want. Therefore, 4 times 1,000 is equal to 4,000 milligrams. And that's how many milligrams of active ingredient will be needed to compound this. So the second part is pretty straightforward. Here we ask how many grams of base would be needed to compound the 200 grams. Well, that can be calculated using a simple formula of active plus base equals total. So before, in problem 1, we did ask specifically how many milligrams, but that can just as easily be translated to grams here. So for our active, we know that there are 4 grams based on our answer from the first part. What is in question is our base. We don't know this, but we do know the total, and the total is 200 grams, as stated here. So we know that 4 plus something is going to give us 200 grams. Well, this is just a simple algebra problem. So we're going to go ahead and subtract 4 from both sides, leaving us on this side with 196. And that is our answer. So when we combine 4 grams of active ibuprofen powder with 196 grams of base, we'll get a 200 gram compound. And there you have it. Hi everyone, and welcome to another MHA math video. Today we're going to be encountering a problem that most pharmacy technicians encounter on their national exam. It's called an alligation problem. The problem reads as follows. How can you make 900 mLs of 30% alcohol from the 20% alcohol and 50% alcohol you have in stock? It's really very simple. Let's go to the board. So whenever you encounter an alligation problem, you want to set it up like tic-tac-toe. Once you have your tic-tac-toe board written, you need to fill in the blanks. So in the top left-hand corner, you want to put your highest concentration. In this case, you have 50. In the middle, you want to put your middle concentration, or the thing you're looking for. In this case, you're looking for 30. Then, on the bottom, you want to list your lowest strength. In this case, it's going to be 20%. Then, once you have these filled in, you want to find the absolute difference. So the absolute difference between 20 and 30 is 10. And then the absolute difference between 50 and 30 is 20. Perfect. So now that you have these numbers, we want to add them together. So 10 plus 20 is going to give us 30. Perfect. But 30 what? What does that really mean? Well, 30 then becomes our denominator to solve the problem. So something over 30, and then something over 30. But what are these somethings? Well, if we look at the problem, we can see that it's actually divided in half. The top part and the bottom part. In this case, the 10 becomes this numerator, and the 20 becomes this numerator. So we're left with 10 over 30 and 20 over 30. So 10 over 30, which comes from here, is going to reduce to 1/3. Then 20 over 30, which comes from here, is going to become 2/3. Perfect. But again, we ask ourselves, 1/3 of what? 2/3 of what? What does that mean? Well, the answer lies in the quantity that we want to calculate. In this case, the quantity that we want to calculate is 900 mLs. So, 1/3 times 900 mLs is going to give us 300 mLs. And then 2/3 of 900 mLs is going to give us 600 mLs. We're almost done. So this 1/3, it came from this part. And remember how I told you this is kind of divided in half, the top part and the lower part? This 1/3 corresponds to the higher strength. So this 1/3 corresponds to the 50%. Similarly, this 2/3 corresponds to the lower part, in which case the lower part here is 20%. So, in order to compound 900 mLs of 30% alcohol from 20% and 50%, you would need to combine 300 mLs of 50% and 600 mLs of 20%. And there you have it.